lecture, very important topics comes the bandwidth dilemma. There are various ways to describe a bandwidth. Okay, let's see if I can open a note. Okay, so this is for bandwidth. This class will discuss about bandwidth. Guys, this presentation is actually already uploaded. This presentation is already uploaded. So there is not much, lots of text, but I will try to explain what they mean. Okay. So this is our review class 1. Review class 1, where we will discuss about bandwidth. Now, for bandwidth, one of the definition comes as an absolute bandwidth. Absolute bandwidth. What does it mean? Imagine we have a signal. It's a rectangular signal. Actually, this is actually the same pulse shaped signal we just used. This is a rectangular signal which can be expressed or this way. This is our signal. So this is in frequency domain, from 0 to twice W. So omega. This is A by twice omega. So width is actually not omega. This is W. This is W. Width. You see here in this signal there is nothing. So what is the width of this one? 2W of this width of this signal. So up to W or minus W, sorry, there is nothing. Here this amplitude is 0, or here this is amplitude is 0. Right? So for this signal, the signal has to be, we will express the signal as its absolute bandwidth. So what is absolute bandwidth? The whole bandwidth, this one, from here to here. That is its absolute bandwidth. Right? Can you express this signal to time domain, guys? Xt? Probably. Repeat with me how I express this signal to time domain, inverse Fourier. Help me to write it. This is a frequency domain signal. I want to convert it to the time domain. Guys, tell me what is the bandwidth here. So how to express it?
We have the integral.
Integral?
Yeah, minus omega.
Minus W to W. Yeah.
Yes. We have the amplitude.
Amplitude. Yeah.
Yeah, we have to multiply it by the function, and e to the power, yeah, minus, there is minus.
So if I do this one, I will actually end up with time domain.
Minus.
Sorry?
Minus,
no.
Minus.
When we do the Fourier transform, then we do the minus. Then it will be minus. Now it's inverse Fourier. So there will be, remember, So it's easy to solve this equation. This amplitude will be in front, A by twice W minus W by W e to the power j theta. You know the derivative, right? So you will be having it like, okay, just we do the e to the power j 2 pi ft, because it's not the same amount, so we have to give the punishment j 2 pi t because it's in respect to f, so we are not writing f, so minus isn't it, if we solve it, right? So you will actually end up with a sinc function, some sinc function, some sinc. The solution will be something like this. Now this one, whenever this signal actually we express by its limit, upper and lower limit, this one is the bandwidth we express is actually we called it absolute bandwidth or strictly band limited signal. So this kind of signal is called strictly band limited signal. Band limited signal. So for strictly band limited signal, this is the only definition you can have, absolute bandwidth, because this is strictly band limited signal. If it's not, then you can have other signal, other definition. For example, I gave you an, for example, our previous, let us go to our previous, this is our review class, right? Review 1. In our previous classes, we have seen the here when we make the solution, sinc function, where yeah, this one. Can anyone, we have already drawn the signal. You see, this is the sinc function, right? So I will write this sinc function again. Let's write this sinc function again. Okay, let's draw the sinc function again. This is sinc function, right? Our previous expression was T sinc ft, which was actually xf. So this is an xf function. Now, this is not a band limited signal like the previous one. Okay, so if this is not a band limited signal, how to express it? How we express the bandwidth? So there are several definitions. One of the definition is called half power. What is half power? Half power means here is the maximum power. For example, here is the maximum power of this signal. Half power is here. If we go to the 3 dB, or we call it minus 3 dB, this here is the half power. So the frequency is the lower and higher frequency, FH. This FH minus L lower, this is called the half power bandwidth. This bandwidth like 3 dB. We can also express for not strictly band limited signal, we can express other definition, and one of the definitions is a half power bandwidth. And there are some other definition you can see in our presentation. Bonded power spectral density. And what is bonded power spectral density? A popular method for specifying bandwidth is to bonded, where a fixed value will be taken. What it mean actually? For example, here is a maximum value. Some maximum value is here. Now you will define, okay, what is the minus 50? Like if you go minus 50 dB, what is the bandwidth? So probably minus 50 will be here. So here, so that bandwidth is the bonded bandwidth. So you see, you are giving a boundary. you are giving, okay, give me a bandwidth at minus 50 dB. So you are giving a boundary. That's why it's called boundary bandwidth. It can have a, so we have a half power bandwidth, we have a boundary bandwidth, we can have fractional bandwidth. Fractional bandwidth. Fractional bandwidth is nothing but the 99% power. What does it mean, 99% power? For example, where, so you will reduce yourself, from here and see where the 99% power constraints. For example, up to this point, 99% power contains. So this will be your fractional bandwidth. Okay. The most important is the noise equivalent bandwidth. This is very widely used because the noise is the guy who disturbs us a lot. That's why we use our communication system. Noise equivalent bandwidth is actually very popular. So remember how our white noise looks like, very common, white noise. Here noise equivalent bandwidth means actually this bandwidth is actually measured in terms of white noise. What is a white noise? You have seen in your random signal processing classes, courses, in RSP. What is a white noise? White means what? White comes from the light, white light. White light means where all the frequencies are there. So if I draw the power spectral density of a white light, it looks like this. Like everywhere it has a value. Got it? And usually we express it by eta 0 by 2. That's actually our white noise expression. Okay. Now in a noise equivalent bandwidth, we took a ideal low pass filter. Ideal low pass filter. Where do we will be using this ideal low pass filter? We'll be using this ideal low pass filter in this block diagram. Remember, I gave you this block diagram here. Filtering. So if I zoomed in, low pass filter will be used in the baseband. Here in this portion. After our information signal, baseband signal, there will be a low pass filter at this point. At this point, a low pass filter is used. Okay. Now imagine we have an ideal low pass filter. We give a white noise as an input. Imagine we give that white noise as a S. Give it a name. Give it as a name S, because it's a in frequency domain, and our output will be S of Y. This noise spectral is actually here. If you give it here, what our aim is to find what is the expected value or average power, expected value of noise, for example, or average power, whatever, average power. Now we say okay, average power N. This is output power here. So N output 1 for first. This is our first case, or this is the one actually we are calculating here. What will be our average power, output power? Our average, this output will be, what is the input here? What is the input? Eta 0 by 2. Eta 0 by 2. This is actually our input. Eta 0 by 2 input. And this is our ideal low pass filter. So let's see what its characteristics look like. What a ideal low pass filter looks like. Probably this, right? Because the ideal is have a very sharp bending, right? This is our HF is our transfer function. If it would be a practical, what it happens low pass, so it would be like this. It would be a practical, but it ideal, so this transition is fast. This transition, this amount, this is fast, like very sharp cut. That's in ideal. Okay, so for ideal, what is the bandwidth? So it's start from minus B to B. Just here is minus B to B. And what is transfer function? HF. So its transfer function is HF. What I write it here, guys? I write it this relation, the power spectral density of output and power spectral density of input. Power spectral density of input and power spectral density of output. We know the power spectral density of output is Y. How they will be related? They will be related to the power spectral density of input is X by the transfer function. From where I got this formula? Wiener-Khinchin theorem. Most definitely, you find this formula in your RSP class. So guys, see how RSP course is handy here. So if we solve this equation, we find n0 by 2, eta 0 by 2. So minus b to b, we can write it 0 to b by multiplying by 2. So these 2 and 2 will be crossed. So we have h of f square df. So eta 0. What is hf square? This transfer function, this amount here. So we can define it by h o is height. So it's h o, h of o square b. B is its total bandwidth. What I'm doing here actually, I'm actually taking the whole area. The width is b, height is ho. That's actually our total. What is the total power in this region? Power spectral density. Any power within the signal region is called power spectral density. That's actually we find it. We find it for ideal filter. Now we will find it for practical filter. If our filter is no more ideal, it's a practical now. What will happen? I give the same noise, I give the same output. So this will be our N output 2. This is our same white noise. What will happen if I give the same white noise? Now you see our response changes. Before we had a sharp cut.
Sir.
Yeah.
Sorry to interrupt, sir. We have another class from now, sir. 3:15. It's already 3:17.
Really?
Yes.
Okay. So 2 minutes.
Okay, sir.
Okay. So our I'm just finishing. So for practical filter, the response is like this. So the practical filter, the response is like this. Okay. So in practical filter, we will get the same equation. N out 2 will be same equation previously, n eta 0 by 2 h f square df. Now the noise equivalent bandwidth is say, okay, so this is the n out. Okay, what was the previous one? N ideal. N out 1 was our noise output. if noise output was N1, if you want to use a practical, then your value will be N out 2. For what bandwidth? Means this is actually for practical, right? Practical. This is for ideal. Means actually we will use the ideal filter, but we will use the bandwidth for the practical. That bandwidth actually called the noise equivalent bandwidth. Noise equivalent bandwidth. Actually, the details are here. I discuss it from here. Noise equivalent bandwidth, probably here. Equivalent noise equivalent bandwidth here. Okay, guys, that's all. You have a class now. So see you in the next class.